Dear organizers, teachers, and researchers, good afternoon. I'm honored to be here with you all. I am the speaker of this topic. My name is Fu Zhenpeng from China, currently studying in Wuhan Textile University, School of Computer and Artificial Intelligence. The topic of this talk is boosting vision transformer for low-resolution Borehole image stitching through algebraic multigrid. And I will present our work in these three areas. The first being the introduction to the work, the second being the methodology and the data collection, and the third being the experimental results. First, in recent years, in-hole accidents have often occurred in core drilling projects, which not only affect the efficiency of drilling, but also increase the cost of drilling and become a major factor limiting the smooth progress of core drilling projects. In the petroleum, geologic, coal, and construction industries, where core drilling is still being carried out. In-hole accidents such as rock cracks, sand floor, water leakage, broken roads are common and can lead directly to the collapse of the borehole. And because we humans cannot see with the naked eye how the structure inside the rock hole is, and the natural light source cannot go deeper, and the rock hole is not big enough to support an adult to go down and explore. So video of the borehole is a regular means to understand the state of the surrounding rock during the construction of underground projects. The video of the borehole walls can be collected and analyzed to gain a full understanding of the fracture development in the surrounding rock and thus evaluate the safety of the project. So the current borehole video processing solution is at the manual stage. However, manual marking of cracks, fissures, quicksand, etc. is inefficient, subjective, and inaccurate. Secondly, due to the low resolution of the filmed video, data interference from external and internal light source, as presented in this small video on the left. It has a great impact on the researcher's observation of the video. Finally, manual frame-by-frame comparison of the image stitching is not only inefficient and slow, but also results in very unsatisfactory stitching results, such as stitching schism, distortion, and blurring. So in summary, it is undesirable to manually mark all the borehole videos, so the computer, instead of manual operation on the borehole wall video analysis research, can not only save manual time but also improve the video processing accuracy, which has important industrial value and significance. Therefore, to solve the above problem, we propose the enhanced with transformer low-resolution Borehole image stitching framework through algebraic multigrid. The main research elements as shown in Figure 1, which include the image pre-processing model, image stitching model, and the data collection. So first up is our image pre-processing stage. As shown in Figure 2, the contrast of the image is changed by using the gamma transform to increase the contrast of underexposed images and decreases the contrast of overexposed images. Then the image is subjected to Canny detection and the gradient of all pixels is calculated using the Sobel operator to achieve the most accurate identification of the central of the cycle possible. The resulting cycle center is finally expanded by equation 1 for the warp and weft of the fisheye image to obtain a rectangle to be stitched together. In the second step, the flattened image blocked after segmentation and position encoding, which are fed into the image stitching model we have designed, and the image is reconstructed using an algebraic multigrid, and the mean squared error MSE between the reconstructed image and the original image is calculated, aided by the multi-head attention in the transformer to filter out future blocks within a threshold range and decoded to obtain matching coordinates. The longitudinal displacement difference delta p is obtained using the affine transformation, and the image is stitched together. Equation 2 is used to calculate the mean square error between the original image and the reconstructed image. The equation 3 is used to calculate the longitudinal displacement after affine transformation, the delta p. And then finally, we have collected a total 120,000 images of different engineering sites, such as 26,000 images of granite drilling sites, 21,000 images of coal mine exploration boreholes, and 56,000 images of rock sample boreholes from the Toba Tower power station as a dataset with resolutions of 480p and 720p. This dataset allows our method to be better adapted to different geotechnical environments. So as we can see, the experimental results. The first is Figure 5, which shows a comparison of our results for the cycle center, which correspond to parts of A, B, and C. A is images affected by sunlight. The B is image affected by sunlight and cold light. C is the image only affected by the cold light. And it can be seen that our algorithm identifies the cycle centers within an acceptable error range. The OGHT algorithm identifies the cycle centers, but with the large error, and the HCDI method does not identify the cycle centers on the corresponding image. In contrast, our proposed method is better able to identify the center of the cycle for images with large changes in illumination intensity. Second, in order to verify its monotonicity, this paper used Gaussian filtering to process images subjected to different illumination disturbances. The experimental result shows that as the standard deviation increases from 0 to 2, the image is gradually blurred and the MSE value gradually decreases, like this figure 6, which satisfies the criterion of monotonicity. And finally, in order to demonstrate that our method works well for low-resolution geotechnical Borehole image staging, we performed the following ablation experiments as shown in figure 7. The first column shows the splicing results corresponding to the method which is proposed in this paper. That's our method. The second column shows the experimental results which obtained without calculating the longitudinal displacement delta p and using the affine transformation. The third column shows the splicing result obtained when the MSE threshold is reduced by 20, which means our method is more better. Okay, that concludes my report. Thank you for listening.